Hello, physics students. In this second part of the video, we're going to zoom in on uniform acceleration. We already talked about how constant velocity means the velocity remains constant for the whole entire interval of times. Acceleration is similar, except that the acceleration remains constant. So I'm going to use the fact that the acceleration is 3 meters per second every second. And it's uniform because the ramp shape doesn't change, twist, curve, or anything. So that means the acceleration in the beginning is the same as the acceleration in the middle and is the same as the acceleration in the end. So for the whole time, it's going to accelerate at 3 meters per second every second. All right, so that's kind of the definition of uniform acceleration. We're going to look at what that means in terms of the velocity, the acceleration, and the displacement in each of the intervals of time. All right, so we already know that the acceleration is going to remain the same. So we can already write that in, 3 meters per second per second. Now another way to write that is 3 meters per second squared. So I'll just do that here. And 3 meters per second squared. Okay, what we want to solve for is how fast is it going at the end of those intervals and how far has it traveled at the end of those intervals. So to do that, we're going to kind of use some equations, but conceptually, I want to compare our graphs first. So when we have uniform acceleration, that means that the acceleration is positive. In this case, we're at a positive 3 meters per second squared, or 3 meters per second every second. Just like on the velocity over here, it was uniform and constant, so it was a flat line, but it was at 3 meters per second, so the velocity didn't change. In our example here, the acceleration isn't going to change. But what that means is the velocity will change at a constant rate. Okay, so that's going to have a look like this, just like our distance did before. And we're going to figure out what does that mean in terms of the displacement or the distance versus time graph. I'll give you a big clue. This is where it's going to have a curve. Okay, so when we just look at the graphs, when there is uniform acceleration, that means that the acceleration is constant, so there's going to be a flat line for acceleration. In fact, there will never be a slant or a curve in your acceleration for these units. We are always dealing with uniform acceleration. So if you get something different for your acceleration graph, go back and rethink it. If it is a constant positive acceleration, that means it's going to change the velocity at a consistent rate, and the distance graph will be curved like a parabola. All right, so how do we calculate for this? Well, there's a couple different ways, but I want to go back to the definition of acceleration when we talk about our equations. Acceleration is, by definition, the change in velocity over time. So change means the final minus the initial divided by the time. I can rearrange that and I can get an equation that just solves for final velocity, where my final velocity is equal to the initial velocity plus acceleration times time. Now let's see that in action. If we want to find the velocity after 1 second, we can use that equation. All right, so we'll say that the velocity at the beginning was 0 meters per second. And we haven't traveled anywhere yet, so that's also 0 meters per second. So we're going to solve for this right here. We're going to say, what at 1 second, how fast is it going? And at 2 seconds, how fast is it going? All right. Now I can do that by plugging in to my equation right here, VF equals VI plus A times T. So the first second is easy because our initial velocity was 0. So if you notice in my equation here, where I see VI, that means initial velocity, I'm putting in 0 because we're starting from rest. Okay, so that's a big hidden variable, we call it. If it starts from rest, or if it starts, whatever the clue is in the reading, a lot of times it's starting from rest, your initial velocity is 0. We call that a hidden value because it's not going to explicitly tell you in the problem. Okay, but it's really important. So we're still going to plug that in, and then we're going to use the acceleration. In this case, it's 3 meters per second squared times the time, 1 second. That gives us a velocity after 1 second of 3 meters per second. All right, so I'm going to go ahead and put that in at the top here. We're going to put that in right after 1 second. We will be going 3 meters per second. Now, how fast are we going at 2? Well, you already know at 2 seconds, the ball is continuing to roll down the hill. It's not like it starts from rest again. It's going to build on the velocity it already has. So it's going to build onto the 3 meters per second and accelerate for that distance, okay, for that amount of time. So we can use our equation again, but now we have an initial velocity. I'm going to take the 3 meters per second from before and plug it in right here for the initial velocity at that interval, plus the 3 meters per second squared, the acceleration, times the time that we're looking for. We're looking for it at 2 seconds. That gives me 3 meters per second plus 3 times 2 is 6. So I get a total of 9 meters per second after that second. All right, so I'm sorry for all the scrolling here. I'm trying to compare these two things. All right, so this one is then 9 meters per second is the velocity. All right, I want you to pause the video and do the third one. All right, so at 3 seconds, what is the velocity? Pause the video, and when you're ready, unpause it, and we will take a look at it together. All right, so to find that final velocity, I'm going to take what was before, so the 9 plus 3 times 3. So 9 plus 9 is going to give me 18 for that final velocity over here, 18 meters per second. Okay, now we're going to take a look at displacement. How far will it travel? We know because it's uniformly accelerating, the distance in between each of these seconds should increase, right? And that's why we see a parabola here. At each of the seconds, it's going to increase. If these were ticks of time, it's going to increase the amount of distance in between each of them. Whereas the velocity at each tick of time, that velocity interval stayed consistent. So we have the 0, the 3, 9, 18, and so on and so forth. Okay. Now what we're going to take a look at then is to find distance, we're going to need another equation. And in fact, when I rearrange and I plug into the acceleration equation and do a little bit of math, we actually end up with two equations that can be used to solve for displacement. They both work. So I'm going to show you how these work together, and we should be getting the same answer. This one, if you know the initial and final velocity, you're going to divide by 2, so take the average velocity times the time, which is similar to this equation here, except you're not using the velocity at the end of the interval, you're using it as an average. Because you know in the beginning you're going a little slower, at the end of the interval you're going a little faster, so you need to use an average velocity times the time. This one accounts for that as well. But if we use the acceleration instead of the final velocity. So if you don't know the final velocity, you can use this equation. Since we know a lot of things in our example, we could use either one of those in order to find out the displacement. All right, so let's take a look at that. At 1 second, and I'm going to show you just two of those equations. So the first equation is the average velocity times the time. The second one is the initial velocity times time plus 1/2 at squared. And notice you get the same answer. So at 1 second, if I plug this in, we started at 0, we're ending at 3, dividing by 2, that gives me 1.5 times 1 second, gives me 1.5 meters. Similarly, the initial velocity is 0 times 1, so that term goes away, and 3 meters per second is my acceleration. Half of that is 1.5 times 1 squared, or 1, gives me still 1.5. So I know for sure, checking it two ways, that the distance after 1 second should be 1.5 meters traveled. All right. Well, what about 2 seconds? If it maintains that acceleration, how far will it have traveled after 2 meters? Well, we're going to use the same kind of idea, right? I'm going to plug in the velocity after 2 meters, which was 9, plus the velocity at the start, which was 3, divided by 2, gives me my average. That times 2 is going to give me 12 meters. Now I can do the same thing with the initial velocity, which was 3 times 2, because remember we're doing it at the interval of 2, plus 1/2 at squared. 1/2 times 3 times 2 squared, which is 4. So that 4 times 1.5 gives me 6. 6 plus 6 gives me 12. So in both cases, we get 12 meters at the end of our second interval. All right, so then I have 12 meters to put in right here. Sorry. 12 meters. All right, so pause the video right now, and I'm going to have you figure out what is the displacement at the end of 3 seconds, okay? And you can use whichever method that you would like, but solve for the displacement at the end of 3 seconds, all right? And then when you're ready, unpause, and we'll work through it together. Okay, welcome back. Method 1, we're going to use the average velocity. So we know at that interval it was 18 plus 9. So that 18 plus 9, and then divide that by 2 times my 3 seconds. So I get 40.5 using the first method, meters. Now I'm going to try it with the second method, the 1/2 v or initial velocity times time. So in this case, the initial velocity was 9 times my time, which is 3 seconds. And then I'm going to add that to 1/2 times acceleration times time squared. And I get 40.5. So 40.5 should be your answer in meters. Either way works, double checking your math. Okay, so just to sum up, the difference between constant velocity and uniform acceleration, the constant velocity maintains an equal distance interval between each of the seconds. The velocity does not change because it's constant, and because it's constant, the acceleration is 0, and the distance interval is consistent. For uniform acceleration, the acceleration stays the same, the velocity increases at a steady rate, and the displacement is a curve, like a parabola. All right. If you have any questions about this, please reach out, let me know. My last comment is there is a distinct dividing line between these two, and that's why we talk about it so much. So you can only use the v equals d over t, so only using this equation when there is a constant velocity. It doesn't work when there's uniform acceleration. Likewise, you can only use these equations when there is uniform acceleration, and you can't when there's constant. So the first question you should ask yourself, and please put this in your notes, is it constant velocity or is it uniform acceleration? Checking that will guide you to the right equations every time. Thanks, and have a